Right now, somewhere in your body, a blood vessel is being repaired. A tiny injury, invisible to you, has triggered a cascade of molecular events so precisely coordinated that it has been called one of the most sophisticated biochemical systems in biology. Platelets arrive. Proteins activate in sequence. A clot forms. The bleeding stops. Every single step in that cascade, from the first activation signal to the final stabilization of the clot, depends on a vitamin. A vitamin so fundamental to the coagulation system that it was named after the German word for coagulation, coagulation. The K in vitamin K stands for blood, but coagulation is only the beginning of what vitamin K does. In the last 3 decades, science has revealed that vitamin K is a cofactor for a family of proteins involved in bone mineralization, arterial calcification prevention, glucose metabolism, and, most recently, brain function. Vitamin K is not a single-purpose vitamin. It is a molecular switch that activates proteins across at least 5 organ systems. And the majority of people eating a modern Western diet are not getting enough of it. Not just marginally deficient, functionally insufficient, in ways that do not produce obvious symptoms for decades, but that quietly degrade the systems that determine how long and how well you live.
Vitamin K is a fat-soluble vitamin that exists in 2 principal natural forms, and the distinction between them is one of the most important and most poorly communicated facts in nutritional science. Form 1. Vitamin K. 1, known as phylloquinone. Form 2. Vitamin K2, known as menaquinone, itself a family of subtypes, from MK4 through MK13. Vitamin K1 is found primarily in dark leafy green vegetables, spinach, kale, broccoli, Brussels sprouts. It is abundant in the diet of anyone eating vegetables, and it is directed almost exclusively to the liver, where it supports the coagulation system. Vitamin K1 has a very short half-life. It is cleared from circulation within hours. Vitamin K2 is different in almost every way. It is produced by bacteria, found in fermented foods and animal products where bacterial fermentation has occurred. It has a dramatically longer half-life. MK7, the longest chain and most researched form, persists in circulation for 72 hours or more. And crucially, K2 is distributed not just to the liver, but throughout the body, to bone, to arterial walls, to the brain, to the kidneys. The mechanism by which both forms work is the same. They serve as cofactors for an enzyme called vitamin K-dependent carboxylase. This enzyme takes specific proteins, called vitamin K-dependent proteins, or GLA proteins, and adds a carboxyl group to particular glutamate residues. This carboxylation is what activates the protein. Without vitamin K, these proteins remain inactive, called undercarboxylated, regardless of whether the proteins themselves are present in adequate quantities. The discovery of vitamin K begins, like many vitamin discoveries, with a disease in animals. In 1929, the Danish biochemist Henrik Dam was studying cholesterol metabolism in chickens fed a fat-free diet. The chickens began to hemorrhage spontaneously, bleeding into muscle and under the skin without any injury to cause it. The fat-free diet had removed something essential. Dam identified the missing factor as a fat-soluble compound he called coagulation's vitamin, the coagulation vitamin. It was abbreviated to vitamin K. In 1935, he isolated it. In 1939, the American chemist Edward Doisy determined its chemical structure and synthesized it, work for which both Dam and Doisy shared the 1943 Nobel Prize in Physiology or Medicine. For the following 4 decades, vitamin K was understood almost entirely as a clotting vitamin. Its role was clear, its mechanism was worked out, and, because obvious clinical deficiency was rare in healthy adults, it attracted relatively little research attention. Then, in the 1970s and 1980s, everything changed. Researchers began identifying a new class of proteins, outside the coagulation system, that also required vitamin K for activation. The first and most important was osteocalcin. a protein produced by bone-forming cells that, when properly carboxylated by vitamin K, binds calcium and directs it into bone matrix. The discovery reframed vitamin K from a clotting specialist into something much larger, a master activator of calcium-regulating proteins. Then came the arterial discovery. A protein called matrix GLA protein, MGP, was found to be the most potent known inhibitor of arterial calcification. MGP is produced in arterial smooth muscle cells and works by binding calcium and preventing it from depositing in arterial walls. But MGP requires vitamin K2 for activation. Without adequate K2, MGP remains undercarboxylated, inactive, and calcium deposits freely in arterial tissue. This was the finding that connected vitamin K deficiency to cardiovascular disease.
Vitamin K's functions are now understood to span at least 5 organ systems, and new GLA proteins are still being characterized. Let us work through each domain with precision. Coagulation, the original function. The coagulation cascade requires at least 4 clotting factors, factors 2, 7, 9, and 10, that are vitamin K-dependent proteins. Additionally, the natural anticoagulants, protein C and protein S, are also vitamin K-dependent. This means vitamin K does not simply promote clotting. It regulates the entire balance between coagulation and anticoagulation. A vitamin K deficiency impairs both clotting and the body's ability to control excessive clotting. Bone health, the osteocalcin system. Osteocalcin is produced exclusively by osteoblasts, the cells that build bone. In its carboxylated form, it is essential for binding calcium and anchoring it into the hydroxyapatite crystal structure of bone. Studies consistently show that higher vitamin K2 intake is associated with lower rates of hip fracture, vertebral fracture, and osteoporosis-related bone loss. In Japan, a high-dose MK4 supplement, Menaquinone, is an approved pharmaceutical treatment for osteoporosis. Arterial health, the MGP system. Matrix GLA protein requires vitamin K2, specifically the longer-chain menaquinones MK7 and MK8, for activation. The Rotterdam Study, which followed 4,807 Dutch adults over 10 years, found that the highest total of dietary K2 intake was associated with a 57% lower risk of aortic calcification and a 52% lower risk of cardiovascular mortality compared to the lowest tertile. No such association was found for vitamin K1. The tissue distribution of K2, reaching the arterial wall, makes this mechanistically coherent. Glucose metabolism. Osteocalcin, in addition to its role in bone mineralization, acts as a hormone when undercarboxylated. The undercarboxylated form of osteocalcin signals to the pancreas to increase insulin secretion and to fat cells to increase insulin sensitivity. This bidirectional relationship between vitamin K status, osteocalcin carboxylation, and glucose metabolism represents an entirely new understanding of how bone and metabolic function are interconnected. Brain health. Vitamin K-dependent proteins have been identified in the brain, including GAS6, growth arrest-specific protein 6, and protein S, which promote neuronal survival, myelin maintenance, and microglial regulation. MK4 is the predominant form of vitamin K in the brain and is concentrated in brain regions with high metabolic activity. Emerging research suggests that low vitamin K status is associated with poorer cognitive performance in older adults, and that K2 may have neuroprotective properties through its role in sphingolipid synthesis. Vitamin K deficiency exists on a spectrum. At one extreme, classic hemorrhagic disease, most commonly seen in newborns who have virtually no vitamin K stores at birth, and in patients with severe fat malabsorption disorders. At the other, subclinical insufficiency, the form that is widespread in healthy adults eating modern Western diets, producing no obvious bleeding symptoms but detectable through biomarkers of undercarboxylated proteins. Neonatal, vitamin K. Deficiency bleeding. Newborns are born with extremely low vitamin K stores. The placenta transfers K poorly, breast milk contains modest amounts, and the infant gut microbiome that produces K2 has not yet established itself. Without prophylactic vitamin K injection at birth, approximately 1 in 10,000 newborns develops vitamin K deficiency bleeding, a condition that can cause catastrophic intracranial hemorrhage. The intramuscular vitamin K injection given at birth is one of the most evidence-based and effective preventive interventions in all of medicine. Adult subclinical insufficiency. In healthy adults, frank vitamin K deficiency is rare. But subclinical insufficiency, measurable through the percentage of undercarboxylated osteocalcin and undercarboxylated MGP in the blood, is extremely common, particularly for vitamin K2. Population studies in Europe and the United States consistently find that 70 to 80% of adults have elevated undercarboxylated MGP, indicating that their K2 status is insufficient to fully activate this key arterial protecting protein. Toxicity. Among the fat-soluble vitamins, vitamin K has an extraordinary safety profile. Unlike vitamins A and D, which have well-documented toxicity syndromes at excessive intake, no tolerable upper intake level has been established for vitamin K by most regulatory bodies because no toxicity from food or supplements has been demonstrated in otherwise healthy adults. High-dose MK4 at 45 mg per day, used clinically in Japan for osteoporosis, has been used safely for decades. The warfarin paradox. Warfarin, the world's most widely prescribed anticoagulant for decades, works by blocking vitamin K recycling, thereby preventing the activation of clotting factors. Patients on warfarin are typically told to limit vitamin K intake because eating more K can reduce warfarin's effect. But here is the paradox. By blocking vitamin K recycling throughout the body, not just in the liver, warfarin also blocks MGP activation and osteocalcin carboxylation. Long-term warfarin use is associated with significantly increased arterial calcification and reduced bone density. The drug that prevents dangerous clots may, over time, accelerate arterial hardening.
Where do you get vitamin K, and which form? The answer depends entirely on which form we are discussing. K1 and K2 have fundamentally different food sources, and optimizing intake requires understanding both. Vitamin K1 sources. K1 is found in abundance in dark green vegetables. Kale is the richest. 100 grams of cooked kale provides over 800 micrograms, more than 10 times the adequate intake for adults, which is 90 to 120 micrograms per day. Spinach provides over 500 micrograms per 100 grams cooked. Broccoli, Brussels sprouts, asparagus, and green cabbage are also significant sources. If you eat leafy greens regularly, your K1 intake is almost certainly adequate, and K1 will keep your clotting system fully functional. Vitamin K2 sources, the critical gap. K2 is where most people are deficient because K2 sources are largely absent from modern Western diets. The single richest K2 source in the world is natto, a traditional Japanese fermented soybean product. 100 grams of natto contains over 1,000 micrograms of MK7, far more than any other food source. This is part of why Japanese women, who consume natto regularly, have among the lowest rates of hip fracture and cardiovascular disease in the developed world, despite consuming relatively little dairy.
Aged hard cheeses are the most practical K2 source for Western diets. Gouda, Edam, and Jarlsberg cheeses are produced using bacterial cultures that synthesize menaquinones during fermentation, particularly MK8 and MK9. A 100-gram serving of aged Gouda provides approximately 75 micrograms of K2. Brie and Camembert are also meaningful sources. Egg yolks provide MK4, particularly from pasture-raised hens, whose diet includes vitamin K-rich plants. Chicken liver and other organ meats are among the richest animal sources of MK4. Absorption. Like all fat-soluble vitamins, vitamin K absorption depends entirely on the presence of dietary fat. Eating spinach with no fat virtually no K1 absorbed. Eating spinach dressed with olive oil, absorption increases dramatically. The same applies to K2 from cheese or natto. The fat naturally present in cheese and egg yolk makes K2 absorption from these foods highly efficient. One of the reasons whole food K2 sources are preferable to low-fat alternatives.
Everything we have covered, now made completely actionable. Here is what the science actually supports for food, supplementation, and daily practice. Eat dark leafy greens every day with fat. A single serving of cooked kale, spinach, or broccoli with olive oil covers your vitamin K1 requirement entirely. This is not a supplement strategy. It is a food strategy that also provides fiber, magnesium, folate, and a dozen other nutrients. The fat is not optional. Dress your greens with olive oil or eat them alongside avocado, eggs, or nuts. ADD, a K2, source that works for your palate. For those who enjoy it, eat natto. It is the single highest K2 food in the world, and 2 tablespoons 3 times per week provides extraordinary MK7 intake. For most Western diets, aged hard cheese is the most practical K2 food. 30 to 50 grams of aged Gouda or Jarlsberg 3 to 4 times per week provides meaningful MK8 and MK9. Pasture-raised egg yolks daily add MK4. These are not difficult dietary changes. They are permission to eat foods that were considered indulgent. Consider MK7, supplementation if your diet is low in fermented foods. The most researched supplemental form is MK7 at 90 to 200 micrograms per day, the range used in most positive clinical trials on arterial and bone outcomes. MK7 at this dose has an excellent safety profile. Choose a supplement listing MK7 specifically, not vitamin K2 without a subtype specification. If you are on anticoagulant medication, particularly warfarin, do not supplement vitamin K without discussing it with your physician first. This is non-negotiable. If you are newly pregnant or planning pregnancy, discuss vitamin K status with your midwife or obstetrician. Ensure your newborn receives the intramuscular vitamin K injection at birth. This is one of the highest impact preventive interventions in neonatal medicine, and the evidence supporting it is overwhelming. We began inside a blood vessel, watching a clot form with molecular precision, every step dependent on a vitamin named after the German word for coagulation. We followed that vitamin from Henrik Dam's hemorrhaging chickens in 1929 to a Nobel Prize in 1943. And then we watched science rewrite the story entirely. We saw how vitamin K2, the form largely absent from modern diets, activates the proteins that keep calcium in your bones and out of your arteries. We saw the Rotterdam Study's 57% reduction in aortic calcification. We saw osteocalcin acting as a metabolic hormone. We saw vitamin K2 in the brain, defending neurons, maintaining myelin. Vitamin K is the molecular switch that activates the proteins your body cannot work without. In the coagulation system, in the skeleton, in the arterial wall, in the brain. The switch is simple. What it controls is not. If this video changed how you think about a vitamin you thought you understood, share it. Subscribe for more evidence-based explorations of the molecules that determine your health. And tell us in the comments, will you add natto, aged cheese, or MK7 to your routine this week?